Hello and welcome to Applied Statistics using SPSS, and in this video I will show you how to do simple linear regression in SPSS. And the dataset I've got in front of me has got information about tomato plants, and I will investigate to see if there's a linear relationship between the variables canopy dry weight, which is in this column, and total root dry weight, which is in this column. But the first thing I would like to do is to create a scatter plot of these data, just to have a look at the data and to check to see if we've got a linear relationship between these two variables. So in SPSS we select Graphs and Legacy Dialogues and then Scatter. Then select Simple Scatter and Define. So canopy dry weight is the dependent variable, so I'll put this in the y-axis, and total root dry weight is the independent variable. Then select OK. So here is our output, and we can clearly see that there's a linear relationship between these variables, which satisfies the first assumption of the procedure. So to perform simple linear regression in SPSS, we select Analyze, and then Regression and Linear. So as I mentioned, the dependent variable is canopy dry weight, so I'll move this across to the dependent box, and total root dry weight is the independent variable. And if we click on Statistics, I want to make a remark about the Durbin-Watson test. If the measurements were made over time, we would select this test to check that the residuals are uncorrelated, or in other words, no autocorrelation. But this is not the case in this data set, so we don't have to do this. So if we go back, if we then select Plots, I do want to check to see if the residuals are normally distributed, so I will select histogram and normal probability plot. And I will also plot Z predicted versus Z residual. And in this scatter plot we can check for homoscedasticity, and we can also do a further check for linearity. So if we select continue and then OK. So here is the output, and the first thing I would like to do is to make a remark about the assumptions. So if we scroll down, so this is the histogram of the residuals. So this looks approximately normally distributed, and also if we look at the PP plot, we can see the values are very close or quite close to this straight line. So that satisfies the assumption of normality of the residuals. And then if we look at the scatter plot, what we're looking for in the scatter plot is a random pattern about the line of zero standard residual value, which is what we've got, which satisfies the conditions of homoscedasticity and linearity. Okay, if we now go back to the output tables, so under model summary, we've got the correlation coefficient of 0.885, which is a large value. A perfect positive linear correlation would be a value of 1. So we've got a strong positive correlation. The R-squared value is 0.783. This indicates that 78.3% of the variability in the outcome is accounted for by the model. And next, if we look at the ANOVA table, we can see that this is significant, so we reject the null hypothesis, and the null hypothesis is that the coefficient of the independent variable is 0. So this is further evidence that the model is suitable. And in the next table, here are the coefficients. This is the constant and the coefficient of the independent variable total root dry weight, and we can see that this is a significant value, just further evidence for the suitability of the model. And the final thing I would like to do is to create another scatter plot, but this time superimpose a line of best fit. So again we go back to Graphs, Legacy Dialogues, Scatter, and click on Define, and the axes are labelled as before, so select OK. And if you double click on the graph and then select Elements and Fit Liner Total, then this superimposes the line of best fit, and you can see these are the coefficients that we just saw in the output table. Okay, well I hope you found this video useful and learned something about simple linear regression.